surface plasmons (SBS) are coherent delocalized electron oscillations that exist at the interface between any two materials where the real part of the dielectric function changes sign across the interface, for example a metal dielectric interface, such as a metal sheet in air. SBS have lower energy than bulk or volume plasmons, which quantize the longitudinal electron oscillations about positive ion cores within the bulk of an electron gas or plasma. The charge motion in a surface plasmon always creates electromagnetic fields outside as well as inside the metal. The total excitation, including both the charge motion and associated electromagnetic field, is called either a surface plasmon polariton at a planar interface, or a localized surface plasmon for the closed surface of a small particle. The existence of surface plasmons was first predicted in 1957 by Rufus Ritchie. In the following 2 decades, surface plasmons were extensively studied by many scientists, the foremost of whom were T. Terpenter in the 1950s and 1960s, and Heinz Rether, E. Kretschmann, and A. Otto in the 1960s and 1970s. Information transfer in nanoscale structures, similar to photonics, by means of surface plasmons, is referred to as plasmonics. The excitation of surface plasmons is frequently used in an experimental technique known as surface plasmon resonance (SPR). In SPR, the maximum excitation of surface plasmons are detected by monitoring the reflected power from a prism coupler as a function of incident angle or wavelength. This technique can be used to observe nanometer changes in thickness, density fluctuations, or molecular absorption. Surface plasmon-based circuits have been proposed as a means of overcoming the size limitations of photonic circuits for use in high-performance data processing nano devices. The ability to dynamically control the plasmonic properties of materials in these nano devices is key to their development. A new approach that uses plasmon-plasmon interactions has been demonstrated recently. Here the bulk plasmon resonance is induced or suppressed to manipulate the propagation of light. This approach has been shown to have a high potential for nanoscale light manipulation and the development of a fully CMOS-compatible electro-optical plasmonic modulator, said to be a future key component in chip-scale photonic circuits. Some other surface effects such as surface-enhanced Raman scattering and surface-enhanced fluorescence are induced by surface plasmon of noble metals. Therefore sensors based on surface plasmon were developed. In surface second harmonic generation, the second harmonic signal is proportional to the square of the electric field. The electric field is stronger at the interface because of the surface plasmon, resulting in a nonlinear optical effect. This larger signal is often exploited to produce a stronger second harmonic signal. The wavelength and intensity of the plasmon-related absorption and emission peaks are affected by molecular adsorption that can be used in molecular sensors. For example, a fully operational prototype device detecting casein in milk has been fabricated. The device is based on monitoring changes in plasmon-related absorption of light by a gold layer.